Today we will start a discussion on motion in a plane. Now, to study motion or kinematics, as we have seen, the quantities which are relevant to us, they are the position, displacement, velocity and acceleration. And till the last unit, what we saw was, we saw motion along a straight line. And when we described motion along a straight line, then we took care of the direction by a positive or negative sign. If something was moving along one direction, and if we call that as positive, if it was coming back or reversing the direction, if we said this as positive, we call the coming back direction as negative. But now we will extend the discussion to 2 or 3 dimensional motion. So, we will extend this to 2 or 3 dimensional motion, and when we do this, then the direction has to be specified in a general way. In 1 dimensional motion, the direction was specified by the plus or minus sign, but now it has to be a general way, and this we do using quantities called vectors. So, therefore, the first part of study of motion in a plane will actually be studying about vectors. So, before we describe, what we will see here is how do we add vectors, we will see how to subtract vectors, we will see how to multiply a vector with a scalar. Now, I have not introduced the term scalar. Scalar, I will show, is something which is got just a magnitude, or rather than scalar, we could say if we have a real number, how do we multiply vector with a real number. Now, the question which may also come to you is, how do we multiply vectors, can we multiply them, and that we will refrain from answering that question in this unit. Later on we will talk about 2 types of multiplication of vectors, and that will follow after some time. And after we do the vectors, then we will look at motion of a body in a plane, and when this motion of a body in a plane takes place with constant acceleration. Now, because this is motion in a plane, it will have multiple directions, and if acceleration is constant, then this is what leads us to a special type of motion which we call as projectile motion, and which we will explain. And finally, in the last part of this unit, we will study circular motion, a point which is moving, and as it moves it traces a circular path. So, these are things which we will study in this unit. So, we start the discussion of this unit with scalars and vectors. A scalar is a quantity which has a magnitude. So, how much of that quantity is there, that is what represents a scalar, and there is no sense of direction in a scalar. So, this is basically a scalar quantity is specified by a single number in a particular sets of units. So, it is always any quantity, unless if it is dimensionless, will be specified with a unit. In a scalar quantity, this will be just a single quantity. For example, when we talk of mass of an object, so we say the mass is 1 kilogram or 2 kilogram or 1000 grams, 500 grams, etc. So, there is no sense of direction when we talk of mass. Other quantities which are scalars are temperature of an object. When we measure the temperature, then we say, let us say when we measure someone's body temperature, we say it is 37 degrees centigrade or 98.6 degrees Fahrenheit, the normal temperature of human body we talk of. Again, there is no sense of direction. Even when we talk of motion in a point, then if we look at the quantity which we called as distance or the path length, this was the total distance a point moves when going from A to B, and when we measure the distance, there is no sense of direction involved. So, this quantity is also a scalar, and scalars follow the general or the common rules of algebra, like scalars can be added, addition, subtraction, multiplication and division. Now, addition and subtraction we have seen, we can take two scalars and we can add them or subtract them. When we add or subtract scalars, then the units have to be identical. So, for example, if you have two masses, you can add two masses. But if I have mass and a temperature of a body, now these two things are scalar. Adding mass to a temperature will not give me anything meaningful. So, therefore, that cannot be done when we have addition and subtraction, then the units have to be identical. But when we multiply and divide scalars, so now if suppose I am multiplying a scalar A with a scalar B. Now, scalar A may have its units of A, scalar B will have units of B. Now, the product of this, when I write this as A multiplied by B, the units of the product will be the product of the two dimensions of A and B. So, we can then work it out. As we have seen, when we multiply A and B, then the units of the product will be the units, the product of the dimensions of these two units. And similarly, we can carry out a division of a scalar A by division B. Now, these, when we do the division, these quantities A and B may have different units. And the quotient which we will get, this will be the division of these two units. And for example, let us look at the density. Density is equal to mass divided by the volume. So, now if the units of mass are in kilograms and if the units of volumes are in meter cube, then the units of density would be in kilograms per meter cube. So, this is what we have, and sometimes let us take an example. Suppose we have a rectangle of dimensions A and B, then here when we look at this, if we look at the perimeter of this rectangle, perimeter is equal to 2 times A plus B. So, we are adding up the two scalars here, the two lengths A and B. So, perimeter is equal to 2 times A plus B. If we look at the area, then the area is equal to A times B, and here if A and B are in meters, then perimeter is also in meters. But if we look at the area A times B, then the unit of area will be meter times meter, which is meter square. Now, let us talk about vectors. A vector is a quantity which has, firstly we will talk of, it has a magnitude and it also has a direction. So, vector will have both magnitude and direction. And then there is a second property associated with vector which is very important, and this is that it obeys a specific law of addition which I will describe, and this law of addition we can either call it as the triangle law, we can express it in that term, or we can call it as the parallelogram law of addition. So, a quantity which has a magnitude and a direction, that is the first requisite, and secondly when we add this quantity, two of these quantities, then they have to follow a specific rule. The answers given by both of these will be the same and we will explain this. So, a quantity has to do both of these for it to be qualifying as a vector. So, a vector is because it has two attributes, it has a magnitude and it has a direction. So, therefore, a vector is specified by its magnitude and its direction, and there are many ways of doing this which we will show. Now, to represent a vector, in a textbook normally you will use a bold letter notation. So, in printed text you will find vector being denoted by a bold letter notation, but when we write it then we use a letter with an arrow on top. This is what, so for example, if I write V with a arrow on top, this represents the vector V, and the magnitude of this vector V, this is represented by just the letter V without the arrow, or sometimes we show it in between two parallel bars with a vector V. So, the vector is indicated by the the magnitude of the vector V, this we will write by either V or V without the arrow. Now, one of the vectors which we have seen earlier also, and let us write this, this is the position vector. Suppose a point P is moving along a path. So, at this instant point P is here, at the next instant it is at point at P prime. So, that means at time t the position the particle is at P, at time t prime this is at P prime. So, what we do is to find the position of this, let us choose a coordinate axis. We choose two mutually perpendicular direction, we call them as x and y, the Cartesian axis. The intersection of these is the origin represented by O. Now, what we do is we draw the line. So, we choose x and y which are mutually perpendicular directions, and O is the intersection of x and y called as the origin. So, we will draw this again. We have here x, y, this is O, this is P. Now, the line from O to P if I draw this. So, this along with this direction, this is called R, the position vector of point P. So, this we can write vector R is equal to OP, and because we are going from O to P along a particular direction, so therefore, we represent this as a vector sign. This is the position vector of P at time t. Now, if this is P prime, I can draw a line from O to P prime, and this I can call as the position vector R prime. This is OP prime, this is position vector of P at time t prime. And actually, if I join P to P prime, this is P, this is P prime. If I join them by a straight line, P prime, this is what we will call as the displacement vector for P. So, the distance, this straight line from P to P prime, which has a particular direction going from P to P prime, is the displacement vector. And as we can see, even if the particle is travelling on any path from P to P prime, it is travelling from this path or this path, the displacement vector from P to P prime will always be the same, independent of the path. And it is clear from here that the magnitude of the displacement vector will be less than or equal to the length of the path. So, now let us define, if we have two vectors A and B, then equality of the vectors means, if we say vector A is equal to vector B, then this will mean that magnitude of A is equal to magnitude of B. This is one thing, but because it is a vector quantity and it has two aspects, magnitude and direction. So, this is one, and direction of A must also be equal to direction of B. So, to ensure this, if we have a vector A which we denote by OP, and there is another vector B which we denote by QR. So, now if A is equal to B, then what you do is, to check this, to check if A is equal to B, we shift B, we shift the vector, either of the two vectors, either A or B, parallel to itself. We shift the vector till the two tails touch each other. So, we will shift B, we shift it towards A till O and Q coincide, and then we look at if P and R coincide. If points P and R coincide, then we say the two vectors are equal. If they do not coincide, then the vectors will not be equal. So, till the two tails touch, if the two heads coincide, then we say vector A is equal to vector B. Now, it is possible sometimes that magnitudes of A and B may be equal, and this we will write as A is equal to B, because magnitude of A is A, magnitude of B is B without the vector sign, but vector A may not be equal to vector B, and this will happen, suppose we have vector A like this and a vector B which has the same length, but a different direction. So, now when you shift the tail of B to A, you will get the two tails will be at the same point, but the two heads will not coincide. So, therefore, vector A will not be equal to vector B. So, this is how we define equality of two vectors. Next, we look at multiplication of a vector by a real number. By a real number, and let us say not only a real number, we will make it as a positive. First, we will take a case of positive real number. Let us say the number is lambda. So, lambda is a scalar because it is just a number. So, that means it is just a magnitude, positive real number, and we look at lambda times A, a scalar multiplied by a vector. So, now what we get is this will be a vector. This product which we have, this product is a vector whose direction is the same as the direction of A, but magnitude is lambda times the magnitude of A. So, for example, let us look at this with an example. Suppose I have a vector A and I want to say, I want to write 2A. So, 2A will be a vector which is twice the length of A in the same direction. This will be equal to 2A. Now, lambda, as we said, so lambda A is another vector in the same direction. If lambda is greater than 1, then the magnitude is of the product is bigger, and if lambda is less than 1, then the magnitude is smaller. And if I look at, so the new vector, let us write this R as the product is equal to lambda A. If I take the magnitude of R, which is equal to R, this will be equal to magnitude of lambda A, and this we can write it as lambda times the magnitude of A, or is equal to lambda times A. Now, here we have talked of positive lambda. If lambda is negative, then we get a vector whose direction is opposite to A. It is in the same line, but it is in opposite direction. So, for example, if we have a vector A like this, then a vector of the same length in the opposite direction, we write it as minus A. So, and if I want to have, if there is a vector which is twice the length in the opposite direction, that will be equal to minus 2A. Now, so we are talking of lambda times A. Lambda can have its own dimension, and the dimension of lambda A will be product of dimension of lambda and dimension of A. And actually the way we have described this, if suppose we have a scalar, if there is a scalar beta which divides a vector A, which means you want to write A divided by beta, then this is just a special case of multiplication of a scalar where 1 over beta is lambda. So, therefore, vectors can be multiplied or divided by scalars with this rule. Next comes the key rule which we described in the property of a vector, and that is addition of two vectors, because we said a quantity a quantity is a vector if it follows the addition rule of the vectors. Now, as we said, this addition we can describe by two methods with which we get the same answer. The first of these we call as the triangle law of addition. So, we have a vector A and there is a vector B, and we want to find the vector R which is equal to A plus B. So, here we choose, it is A plus B, we choose vector A, we draw the vector. So, we draw vector A, draw the vector. Now, at the head of A, that means at the tip of A which is at the end, we draw the vector B with its tail at the head of A. So, we have vector, we draw vector B with its tail at the head of vector A. So, we have vector A here, this is A, this is B. So, now the third side of the triangle seen in reverse order. See, we are going from A to B. Now, the third side of the triangle is this side, and what I mean by reverse order is if I continue from A to B, then if I follow the arrows I should be taking this line, I take the reverse order, and this third side, this gives me R which is equal to A plus B. So, this is how we get vector addition from the triangle law. So, this is called the triangle law, that we draw the two vectors in same order, we complete the triangle, and the third side of the triangle in the reverse order gives us the sum of vectors A and B. Now, let us see, we have seen what is A plus B. Let us reverse the order of addition. So, with these two vectors, let us see vector B plus A. So, if I have to do this, then as I have described, first I will draw vector B, and then on the tail of vector B I will draw vector A. So, this was B, this is A, and then I look at the third side in the reverse order. This gives me the vector R1 which is equal to B plus A. Now, what we realize is that vector R1 is nothing but the same as vector R, that is B plus A is equal to A plus B, and this is what we call as the commutative law of vector addition. So, so this is the commutative law of vector addition, and we see this happening with scalars also, that the sum of A plus B is equal to the sum of B plus A. We have a third property if we add three vectors together. So, now let us add up three vectors A, B and C, and this way, as you will see, we can generalize it to adding of more vectors, and sometimes this, as you will see, is called the Polygon Law of Addition. So, here let us see. So, we have a vector A, to that we add vector B, and so now what we are looking at is A plus B, and to that we add C. So, A plus B, if we look at this will be given by this dotted line, and now the third vector C, which has to be added to A plus B, has to be placed at the tail of B. And now when we look at this, if I add A plus B to C, I complete the triangle, and when I look at it in the opposite sense, so this is A plus B, so this vector here, this gives me A plus B plus C. So, we form a polygon of all the vectors which are there, and the last side which will complete this will give us the sum of all the vectors. Now, let us see how this is related to, if suppose we interchange the addition, that means we look at vector A plus B plus C. That means first we add vectors B and C. So, if I add vectors B and C, I will get this dotted line, and I have to take it in the opposite sense. So, A, B, C. So, I will look at this line, this is vector B plus vector C, and when I add this to A, I again get A plus B plus C. So, what we get is vector A plus B plus, added that to C, will be equal to vector A plus the sum of B and C, and this property is called associative property. So, we can add vectors in any order. Now, we also have, if we look at A plus minus A, we add the vector to negative of itself. Let us try to do this. So, this is vector A. Now, at the head of this I place a vector which is minus A, that means I come back to the same point. So, the sum of these two will be now a vector which we call as the 0 vector. So, the result of adding A to minus of itself is a 0 vector. So, what we get is A, and we can also from here reduce A plus the 0 vector gives us A, lambda times any scalar times the 0 vector will give us the 0 vector itself, and a 0 scalar multiplied by a vector A will give us the 0 vector. So, we have defined a 0 vector in this way. And just as we have addition of vectors, if we try to look at subtraction of vectors, then this is that means we are talking of A minus B, then this is just a special case of addition which we can write it as A plus minus of B. So, that means we take vector A and we add it to minus of B, which means reverse of V, that will give us A plus minus B. And now, as we have discussed, we have seen addition using the triangle law. Now, there is a second way, and which is called the Parallelogram Law of Addition of Vectors. And in the parallelogram law, what we do is we arrange vectors A and B with tails coinciding at the same point. Earlier, if you remember, we first placed A, and at the head of A we placed the vector B with its tail coinciding at the head. Now, here what we do is I have a vector A, I want to add this to vector B. So, I will place vector A and vector B with the tails at the same point. Now, these are two sides, or rather two adjacent sides. So, these are two adjacent sides if we look them as adjacent sides of a parallelogram. So, we complete the parallelogram, that means we draw a vector A from B, and from this step we draw another vector which is equivalent to B. So, this is a parallelogram. Then the diagonal of the parallelogram starting from the tail, this diagonal which starts from the common point of these two vectors, this is equal to vector R, which is equal to the sum of A plus B. Sometimes the reason why we are using sin R, because often the sum of these is called the resultant. So, that is why, but you can use any symbol. So, here the diagonal of the parallelogram gives us the sum of vectors A and B, and this is what is termed as the this is how we use addition using parallelogram law of vectors. And you can clearly see here, if you look at the second side, it is a parallelogram. So, this side is nothing but vector B, and so the diagonal which we have got here is nothing but the third side of the triangle if A and B are placed in order, and so therefore, we see that the parallelogram law is nothing but will give the same result as the triangle law of addition. And if we sometimes, as we said, if we want to look at A minus B, so if we have a vector A and this is vector B, we want to find A minus B, then from B on this side if I draw a vector which is opposite, this is minus B, and I complete this triangle. So, this vector will be equal to vector A minus vector B, and this was A and B. So, that is how we can do the subtraction. Okay. And now, what you will realize here is A minus B will not be equal to B minus A. If I have to do B minus A, then this is B, I move in the opposite direction here, I will get this will be minus A, I add these two. So, that means I complete this triangle, I do this. So, in fact, it will fall on the same line, this vector will be equal to B minus A. In fact, it will turn out B minus A will be minus of A minus B. So, they will fall in opposite directions. Now, we also have, if we have a scalar lambda multiplied by sum of A plus B, this will be equal to lambda times A plus lambda times B, and this can be verified. Next, we look at what we call as resolution of vectors. Suppose we have two vectors A and B which are non-zero vectors in different directions in a plane, and we have a third vector A in the same plane. Right now, we are talking of all the vectors lying in the same plane. So, now what we can say is this vector. So, we have a vector A, a vector B. These are in different directions. They need not be perpendicular to each other. They are just two different directions, and we have a third vector A. So, we have three things A, B and A. Now, what we can say is that the vector A can be expressed as a sum of two vectors. Now, what is the speciality of these two vectors? The first of these is A multiplied by a real number, let us say this is lambda, and the second number is vector b multiplied by a real number which is different in general, say mu. So, what we are saying is we can express A as lambda times small a plus mu times small b. So, this we can do, and the way to do this, to understand this, is let vector A be equal to OP. So, this is the vector A which we denote by OP. Then through O we draw a line parallel to A. So, if the original vector A was like this, so through O we draw a line which is parallel to A, and if the original vector B was like this, and through P we draw a line parallel to B. So, now B was in this direction, we draw a line parallel to B. So, now this one will be lambda times A, this one, the second vector, this will be mu times B, because this parallel to B. So, therefore, whatever is the length, that will come in this factor mu, the length magnification factor will come in the factor lambda. So, lambda A plus mu B can be written as vector A, and what we say is that, so once we do this, we say vector A has been resolved along two component vectors lambda A and mu B along A and B. Now, in general, A and B can have any orientations, but they cannot be parallel to each other. So, this is what we call as resolution of vectors. Now, resolution of vector becomes more common if vectors A and B are perpendicular to each other. And here what we have, so before we talk of resolution along perpendicular direction, we first talk of something called a unit vector. A unit vector is a vector of magnitude 1. It has a directional sense, but its magnitude is always unity. And so, we denote a unit vector in general, whenever we will talk about this, we will use a symbol hat, and whenever we use hat, that means we are talking of a vector whose magnitude is 1, and we call it as a unit vector. So, now let us see the Cartesian system. Our Cartesian system, and here we will now extend this to 3 dimensions. So, let us denote a vector A along its 3 dimensions. So, we have, for example, the x axis, the y axis and the z axis. There is a general point P whose coordinates are x, y, z, and if we take the vector from O to P, let us say this as vector A is equal to OP. Now, if we drop a perpendicular from P on the xz plane and let this hit the xz plane at P prime. Now, if we join OP prime, then it is very clear OP prime plus P prime P is equal to OP. Now, if we look at the coordinates of the point P prime, then they will be equal to x 0 z. This is a point in the z plane. So, y coordinate of point P prime will be 0, it is x 0 z. And what we do is, if from point P prime, if we take a perpendicular to the x axis and a perpendicular from P prime to the z axis. So, now this distance here, this will be z, and this distance here will be x, and this x is what we will say is the x will be the x component of the vector OP, z will be the z component of the vector OP, and similarly P prime P, this is in magnitude equal to y. So, this will be the y component of the vector OP. Also, what we see is, suppose if this vector OP makes an angle alpha with the x axis. So, vector OP makes angle alpha with the x axis. I will show it in the figure here. So, OP makes an angle alpha with the x axis, it makes an angle beta with the y axis, and it makes an angle, I will use a third colored pen, it makes an angle gamma with the z axis. Then what we have is the x component, this will be equal to magnitude of OP cosine alpha, y component will be magnitude of OP cosine beta, and the z component will be equal to magnitude of OP cosine gamma. So, these are what we call as the x y. So, this is x component of the vector OP, this is y component of OP, and this is the z component of OP. Now, what we do is we write unit vectors along x, y and z axes. Now, these axes have a fixed direction. So, for a unit vector along x axis, we will use the symbol I. This is very common. For unit vector along y axis, we use the symbol j. For unit vector along the z axis, we use the symbol k. So, that means if these are our x, y and z axis, a vector of length 1 along x axis is I, a vector of length 1 anywhere along the j axis, this will be j, and a vector of length 1 along the z axis will be k. And if I want to find the magnitude of I, magnitude of j and magnitude of k, think about it, obviously all of them have to be 1. And suppose if I have a vector A in some general direction. So, the unit vector along A will be a vector of magnitude, I should not use the word length, I should say of magnitude 1 along the direction of A. This is what we will call as unit vector of A. Either we use a symbol n for this, or sometimes we use E sub A with a hat. E represents a unit vector in many notations, and A is to give the sense of A, and with a hat tells us that it is a unit vector. So, unit vector along any general direction can be written like this, and if that is so, then what you will realize is if vector A, if unit vector along this is n, then vector A can be written as magnitude of A times n, or magnitude of A times n. This is how we will have the unit vector. And let us now take the resolution of vector A along x and y axes. So, let us look at a planar case now. We have a vector A, this is the x axis, this is the y axis. Let the angle between x axis and A be theta. So, now if this is the point P, this is O, OP is nothing but the vector A. So, now if I drop a perpendicular from here, let this point be Px, I drop a perpendicular on the y axis, let this be point Py. Then it is very clear that A, which is equal to OP vector, this is nothing but O times Px plus OPX plus OPY, sorry, not, isko start. Vector A will be equal to OP is equal to OPX plus OPY, where Px and Py are the points on the x and y axis. And OPX, one can write it as A sub x times I, that is the magnitude of OPX, which is the x component of A, times unit vector along along x direction, which is I, and this I can write it as AY times J. So, here what we have is I can write the vector A as AXI plus AYJ, and AX and AY are called the x and y components of A. So, AX and AY are the x and y components of the vector A. Now, we can also, if we want to find the, so we have vector A, we can resolve it as along x and y as AX and AY. So, we see that there are two ways to write a vector A in a plane. The first way is we use the magnitude of A and we specify the angle theta which A makes with x axis. We specify these two things and that gives us the vector A. And the second way is that we compute the x and y components AX and AY, and then we write the vector A as equal to AXI plus AYJ. And from the figure which makes this, it is quite obvious. If this is vector A, it makes an angle theta with the x axis, this is AX, this is AY, then what we have is AX square plus AY square. In fact, AX will be equal to A cos theta, AY will be equal to A sin theta. So, AX square plus AY square is equal to A square cos square theta plus A square sin square theta, which will be equal to A square. And so, therefore, we can write the magnitude of A in terms of AX and AY as AX square plus AY square, and tan theta is equal to AY upon AX. If we look at this figure, this height is AY, this is AX, so tan theta is equal to AY upon AX. And in all these you realize AX and AY can be positive or negative. So, that is how we work out this thing. Now, in the next class we will continue with a bit more on vector. We will look at the analytical method of vector addition in terms of unit vector, and then we will move on to the description of motion in a plane using vector.